Hi, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. I hope you are doing well, and tonight we talk about volcanoes and how they built our world. We will start with the hot early Earth, see how lava made land, how gas from deep inside helped make the air and the oceans, and how ash and rock turned into rich soil. We will visit plate edges, hotspots like Hawaii, and long chains of fire that shaped continents and mountains. We will also look at the big events in history when huge outpourings of lava changed climate and life. No rush, just calm facts and clear ideas. Get comfortable, breathe easy, and let's begin. But before you do that, take a moment to like the video and subscribe to the channel. We are very close to hitting 10 subscribers. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world. And thank you so much for being here. Think of the very young Earth as a place of heat and change. The surface was a wide ocean of melted rock. Space rocks hit often and added more heat. The crust that tried to form was thin and broke again and again. Through those breaks, lava rose and spread. Gas poured out of countless vents. This steady release of gas is called degassing, and it matters because it built the first sky. Water vapor rose into the air along with carbon dioxide and nitrogen and small amounts of other gases. There was almost no oxygen in that first sky. As time passed, the outer layer of the planet cooled. Some of the melted rock turned solid. Water vapor turned into clouds. Rain fell not for days or years, but for ages. Rain filled the low places and made the first oceans. Volcanoes did not only build land, they also made the air and helped to fill the sea. They worked like pressure valves for a hot young world, letting the inside breathe. Deep inside, the planet stayed hot. Warm rock rose slowly and cool rock sank slowly. That slow churn fed new lava to the surface. Even before the pattern of moving plates was set, this deep motion pushed up islands of rock that stood above the sea for a while, and then sank again. Some pieces were light enough to stay afloat. Those pieces were made of rocks that formed from sticky, silica-rich magma. They were the seeds of continents. Over long time, more light rock gathered at their edges. Ash and lava piled up in layers. Parts of the thin early crust sank under its own weight and melted and rose again. The more this happened, the more the surface sorted itself into heavy parts and light parts. Heavy parts became the floors of the deep ocean basins. Light parts became the hearts of continents. While this sorting went on, volcanoes kept feeding the sky. Water from deep rock kept coming. The amount was large enough that the ocean grew and stayed. Gases in the air made a blanket that kept the planet from freezing. The sun was dimmer then, so this blanket was important. All of this was slow if you count in human years, but fast in the life of a world. From a glowing ball, Earth turned into a place with seas and the first stable land. That change happened because heat moved from the inside to the outside, because lava rose and cooled, and because gases escaped from deep rock and made a sky that could hold clouds and rain. Volcanoes were the workers that did this job day after day over deep time, and the ground we stand on today is the result. Earth is layered like a simple cake. A thin crust sits on a much thicker mantle. The mantle is solid rock, yet it can flow very slowly over long time. Below the mantle is the core, partly liquid and very hot. Heat comes up from the core and also from slow decay of natural elements in deep rock. Warm rock expands a little and becomes less dense. It moves upward. Cooler rock above sinks to replace it. This sets up slow rolling motion called mantle flow. The crust is broken into wide plates that ride on top of this flow. Where plates pull apart, new ground is made. Where plates push together, One slab often dives down into the mantle. Where plates slide past each other, you get long faults and many quakes, but usually not much lava. Volcanoes form mainly in three settings. The first setting is where plates pull apart. This happens along mid-ocean ridges under the sea and along rifts on land. When the top is pulled, the pressure on the mantle below drops. Hot mantle can then melt without extra heat. This is called pressure release melting, and it feeds long chains of small volcanoes that build new ocean crust every day. The second setting is where one plate dives under another. This is called subduction. The downgoing plate carries water and other light materials that were locked into seafloor rocks. As the plate sinks and warms, that water escapes into the mantle above and helps it melt. Melt rises and forms arcs of steep volcanoes on the top plate. The Andes and Japan are examples of this process. The third setting is a hotspot. A hotspot is a narrow upwelling of very hot mantle that can sit under a plate far from an edge. Melt from a hotspot builds a line of volcanoes as the plate moves over it. Hawaii is a classic case. Each setting adds land in its own way. Ridges push out new seafloor and slowly move continents around like rafts. Arcs weld small blocks and islands onto the edges of continents and build mountain chains. Hotspots raise piles of lava that can make whole islands or thick plateaus. When you look at a map of the world, the belts and lines of volcanoes mark these settings. They are not random. They show where the deep engine is working right now. Continents are thick, light rafts of rock that float high on the mantle. Their old hearts are called cratons. These hearts are made of hard, dry rocks that have survived for billions of years. How did such rafts form and grow? Volcanoes did much of the work. Where plates dive down under other plates, the wet melt that forms tends to be sticky. Sticky melt cools into light rocks like granite and related types. Light rocks add buoyant material to the base and interior of continents and help them stay afloat. Over long spans of time, many island arcs collide with continents and stick. Each arc brings a slice of light rock and adds it to the edge. This slow, repeated welding is called accretion. You can see the record of this in places like Alaska and the edges of Asia, where whole chains of old volcanic islands now sit on land. At times, rifts cut into continents. Some rifts fail and never become new oceans. Even failed rifts pour out thick sheets of lava that cool into strong layers and add bulk to the base of a continent. Hotspots add land in another way. If a hotspot comes to rest under a continent, it can heat and partly melt the deep roots of that continent. The melt rises and cools into light rock, thickening the raft from below. This is called underplating, when the new material freezes near the base. In every case, water helps. Water lowers the melting point of rock, so places with water present make melt more easily. Water also weakens rocks, so they bend instead of break, which lets continents survive collisions rather than shatter. The proof of this long building lies in ancient belts of volcanic rock now frozen in mountain roots. The Canadian Shield, the Pilbara and Yilgarn cratons in Australia, and the Kaapvaal in southern Africa all preserve these old belts. Later mountain chains like the Appalachians, the Alps, and the Himalaya also hold thick stacks of old volcanic and related rocks squeezed and changed by pressure and heat. If you peel back the soil and the green of forests and the grey of cities, you find that much of what makes a continent high and strong came from long chains of volcanoes that worked like bricklayers. They laid one cooled layer on another. They brought up light material that floats. They welded pieces together. Without that steady work, continents would be smaller, thinner, and easier to sink. Volcanoes breathe out gases from deep rock. Early in Earth history, this breath was rich in water vapor and carbon dioxide, with nitrogen and other gases mixed in. As the planet cooled, water vapor formed clouds and fell as rain. That rain filled basins and made seas. Carbon dioxide stayed in the sky until rocks and later life pulled it down. The way this works forms a slow loop that sets Earth's long-term climate. Volcanoes add carbon dioxide to the air. Rain picks up some of that carbon dioxide and becomes a weak acid. This acid water reacts with rocks during weathering. The reaction makes dissolved substances that rivers carry to the ocean. There, new minerals form and trap carbon. Life also uses carbon to build shells. When shells and minerals sink and get buried, carbon leaves the air for a very long time. In time, some of that buried material is carried down at plate edges and returns to the deep mantle. A small part of it comes back up again as volcanic gas. This loop is the long carbon cycle. It acts like a thermostat. When the planet is cold, weathering slows down, so carbon dioxide can build in the sky from volcanoes and warm the surface. When the planet is warm, weathering speeds up, so carbon dioxide is pulled down faster and the surface cools. This slow balance helped Earth avoid two bad ends. It kept the oceans from freezing solid forever, and it kept them from boiling away. In deep time, ice once spread across much of the planet. With so much of the surface sealed under ice, weathering was weak and could not pull down much carbon dioxide. Volcanic carbon dioxide built up over time and warmed the air enough to melt the ice. On the other side, very warm periods ended as faster weathering pulled the extra carbon dioxide back down. Volcanoes also affect climate in shorter ways. Strong blasts can send sulfur gases high into the sky. These turn into tiny particles that reflect sunlight. The surface cools for a year or two until the particles fall out. Carbon dioxide from single eruptions is small compared to what people now release by burning fuels. But over millions of years, volcanic carbon dioxide is a major force. Volcanoes also add nutrients to the sea and land. Ash brings iron and phosphorus that life can use. In this way, volcanoes have made the air, filled and kept the sea, fed life, and tuned the long climate line of our world. Life needs water, energy, and nutrients. Volcanoes can supply all three. On the ocean floor, where new crust forms or where magma sits near the surface, hot water rises through cracks. These places are called hydrothermal vents. Some vents blast dark hot fluid rich in metals and sulfur. Sunlight never reaches these depths, yet life thrives there. Tiny microbes use the chemical energy in vent fluids as their food. Larger animals build from that base. Many scientists think life may have started in settings like these, where warm rock, water and gas meet, and where there are natural walls and pores that can shelter fragile steps toward life. On land, fresh lava breaks down into fertile soil. Volcanic soils hold water well and are rich in minerals like potassium and phosphorus. Farmers depend on them in many countries. That is why many people live near volcanoes even when there is risk. They accept risk because the land is productive. Ash can also carry nutrients across wide regions. When ash falls into the sea, it can add iron and spark blooms of tiny life that feed larger life. Volcanoes also change habitats. A lava flow can bury a forest in a day, but the new rock cools and cracks and starts the life cycle again. Pioneer plants find small pockets of dust and grow. Insects arrive. Birds bring seeds. Over years and decades, soil forms and a new forest rises. On islands born from lava, this story repeats again and again. Volcanoes also bring hazards that life must work around. Ash clouds can make it hard to breathe and can ground plains. Fast-moving hot flows can sweep down valleys. Gas can pool in low spots. Lakes near volcanoes can release carbon dioxide that displaces air. These are real dangers. Yet even in places that suffer, life tends to return quickly because volcanic ground is a strong base for new growth. In this quiet way, volcanoes erase and write, and the living world reads the new script and grows into it. The result is a planet where fire from below and water from above and life on the surface are linked. Most eruptions are small compared to the size of a continent. Once in a very long while, a planet releases lava on a different scale. Thick curtains of fire pour from long cracks and cover vast regions. These outpourings are called large igneous provinces. They can last hundreds of thousands of years in many pulses. Each pulse sends out huge sheets of lava and large amounts of gas. 3 past events show how powerful this can be. About 252 million years ago, the Siberian traps erupted again and again. The total lava volume was enough to cover several million square kilometers to great depth. Many researchers link this event to the worst mass die-off in the fossil record. The oceans warmed, oxygen levels in deep water fell, toxic gases may have spread from the sea. On land, many kinds of animals and plants vanished. Around 201 million years ago, the Central Atlantic magmatic province erupted as the Atlantic Ocean began to open. Again, many species disappeared. Around 66 million years ago, the Deccan Traps erupted in India over a span that overlaps with a large asteroid impact in what is now Mexico. The impact dealt a sudden blow that helped end the age of non-bird dinosaurs. Many scientists think the Deccan eruptions added long stress before and after the impact by warming the planet and changing ocean chemistry. These lava floods also built tall plateaus and hard layers that still shape landscapes. They changed the sky by adding warming gases like carbon dioxide and cooling gases like sulfur dioxide. Right after big pulses, sulfur particles in the upper air may have cooled the surface. Over longer spans, extra carbon dioxide likely warmed the climate. The balance shifted with time and with the rate of gas release. These rare events show how the deep engine can change the course of life. We do not see such eruptions in human times. They are spaced by many millions of years, but their rock layers are still with us, thick and wide and easy to trace. They are reminders that the same basic process that lays one small lava flow in a single night can, given a wider crack and a longer time, pour enough lava to reshape the world. Far from coasts, a long mountain chain runs through every ocean. This is the mid-ocean ridge. It is not one peak but a broken, winding line of high ground with a trench down the middle. Here plates pull apart. When the top is stretched, the pressure on the hot mantle below drops. Rock that was close to melting now melts a little. This small melt gathers and rises because melt is lighter than solid rock. It collects in shallow pockets, then finds cracks and reaches the sea floor. Cold water chills it fast, and it breaks into round shapes called pillow lavas, like stacked spheres and tubes. Over time, these stacks make new ocean crust, layer on layer. The ridge does not sleep. It makes new crust day and night, year after year. The crust it makes is thin compared to continents, but very wide. As new crust forms, older crust slides away on both sides, like 2 conveyor belts. This slow spread is steady enough that we can measure it. In some places, it is as slow as fingernails growing. In others, it is a few inches a year. The speed changes the shape. Fast ridges have smooth, broad tops. Slow ridges are rugged, with deep valleys and sharp blocks. Heat from the young crust drives hot water through cracks. The water reacts with rock and comes back out at vents. Some vents shoot dark, mineral-rich fluid and build chimneys. Many forms of life gather around these warm spots in the cold deep. The ridge also makes tiny changes to the shape of the oceans. New crust near the ridge is warm and floats a little higher, so sea level measured from the ridge is higher than far away. As crust cools and grows dense, it sinks slightly. The pattern of highs and lows helps set the paths that deep water takes as it moves around the world. The ridge writes a record too. Iron in lava lines up with Earth's magnetic field as the lava cools. When the field flips, the new crust records the new direction. This makes stripes of normal and reversed magnetism on both sides of the ridge, like a tape slowly written from the center out. These stripes are proof that the seafloor spreads. They let us date the crust and see how long the ridge has been at work. While we rarely see these places with our own eyes, they shape the planet. They make most of the crust on Earth. They create the floors of the oceans. They feed warm water and minerals to the deep sea. They push the plates, and the plates carry continents along. Without the quiet, tireless work of ridges, there would be no moving plates, no growth and loss of ocean basins, and the face of Earth would look frozen and old. Instead, it is young in the sea, always renewed from below. On the edge of many oceans, one plate slides down under another. This is a subduction zone. It begins at a trench where the surface bends into a deep groove. The downgoing slab carries cold rock and water-soaked minerals into the hot mantle. As it warms, that water and other light parts separate from the slab and rise into the mantle above. Water makes rock melt more easily. The mantle there gives off small amounts of melt. Melt gathers, rises, and feeds chains of volcanoes on the top plate. These chains are called arcs because they often form a curved line. Think of the Andes along the edge of South America, the Long Island strings from the Aleutians to Japan, or the many cones of the Cascades. The shape and style of these volcanoes reflect the mix of melts they feed on. Ocean crust is dark and rich in iron and magnesium. When it melts a little, then mixes with parts of the top plate and with water from the slab, the melt becomes stickier. Sticky melt traps gas and tends to build steep cones. When pressure from gas grows too high, it can blast the top off in an explosive eruption. Ash and rock rush down valleys. The sea can be pushed aside and return as high waves. These are real hazards for people, which is why scientists watch arcs closely with many tools. But arcs also build land and mountains in a steady way. As the years add up, ash and lava form thick piles. Heat changes old rock into new kinds and welds blocks together. Off the coast, sand and mud scraped from the downgoing slab jam into a wedge and grow the edge of the continent outward. Sometimes parts of the seafloor, like small volcano islands and coral reefs, ride in and stick on. Arcs recycle the crust too. The slab carries some altered ocean crust and sediment down. Some of this material ends up in the deep mantle and will not return for a very long time. In this way, arcs are the places where old seafloor is consumed and new light continental material is created and added to the top world. It is a cycle with many steps. Ocean crust spreads at ridges, ages and cools, grows dense, then sinks at trenches. The sinking slab helps make new melt above it. The melt feeds cones and builds mountains. The mountains wear down, feed rivers, and the rivers carry grains back to the sea. This loop is slow, but over tens of millions of years, it builds the shapes of coasts. It raises high ranges that shape winds and rain, and it sets the stage for life and people on the land nearby. Not all volcanoes sit on plate edges. Some rise over places where the mantle sends up a narrow column of extra hot material. Many scientists call these columns plumes, and the volcano chain above them a hotspot track. A hotspot does not move much compared to the plate above. As the plate drifts, the melt burns a line of volcanoes. The age of the cones grows with distance from the active end. This is why the Hawaiian Islands form a neat chain. The Big Island sits over the melt and erupts today. To the northwest, each older island is more worn, lower, and cut by deep valleys. Farther still, the chain dives under the sea again, as low peaks and then becomes a long bend and another chain heading toward Asia. This bend marks a change in the direction of plate motion long ago. The seafloor keeps the record like a written line. Hotspots can also sit where a ridge is near. Iceland is one such place. There the ridge and the hotspot work together. The result is thicker crust than normal for an ocean, steady lava outpourings, and a whole island built right on the plate boundary. Some hotspots lie under continents. Over long spans they can heat and thin the lower crust, raise the land, and feed many small eruptions spread across wide areas. In rare cases, a very strong pulse from deep below may help start a flood of lava that covers a wide region, like the great lava fields of the past. The rocks from hotspots often carry small signs that hint at deep sources. Tiny amounts of special elements and rare gases can differ from rocks made at ridges or arcs. These small clues are like labels that tell us the melt rose from a different part of Earth's inside. Hotspots teach us that the mantle is not the same everywhere. It has warm lanes and cooler lanes, places where heat escapes in columns, and places where the flow is sideways and slow. For people, hotspots matter in direct ways. They build islands in the sea where none would exist. They make soils that hold water and grow crops even when the land is young. They can drive geysers and hot springs on land that bring heat to homes and baths. They also remind us that plates are rafts, not roots. The land under our feet rides on moving rock. Where the raft passes over a fixed flame, it is marked with a trail of fire, easy to follow even after many millions of years have passed. Some of the largest eruptions on land do not build a cone, they take one away. In these systems, sticky magma collects in a wide chamber a few miles below the surface. Over time, gas in the magma builds pressure. The roof of the chamber bulges upward. Small eruptions and hot ground can last for years or centuries. Then, in a short time, the chamber empties so fast that the roof cannot hold its own weight. It drops. The surface collapses into a broad, low basin with steep walls. This is a caldera. The eruption throws huge volumes of ash and hot gas into the sky. The ash falls as a blanket over a vast area. Near the source, hot ash and gas race outward as dense clouds that flow along the ground and fill valleys. These flows cool into thick, hard layers that can stand as cliffs. The air can darken for days or weeks. Sunlight at the ground weakens. If the blast is large enough, tiny particles spread high in the sky around the world and cool the surface for a short time. Famous modern places with caldera histories include Taupo in New Zealand and Yellowstone in North America. The word supervolcano is often used for these huge events. The word can lead to fear, but the truth is both simple and calming. Such eruptions are very rare on human timescales. In most years and centuries, the signs we see are small things. The ground may rise or fall a little as magma and water shift. Hot springs change flow and color. Steam vents breathe. Small quakes tap out the motion of fluids and rock. These are watched by scientists with many tools. Networks of ground stations, satellites that can see tiny changes in height, gas sensors, and local observers all help build a picture. If signs grow, warnings can be given. If signs fade, people can relax again. Calderas are not only about danger. After the main event, the basin can hold lakes and rich soils. New rhyolite domes can rise slowly, each one a small pulse that releases pressure. The long, low shape can catch rain and snow and focus water into rivers. In many parts of the world, caldera lands are farms, forests, and quiet towns. They are also windows into the crust, where we can read the story of how sticky magma stores and moves, how gas builds pressure, and how a surface can drop and then heal over centuries with new rock and green growth. Volcanoes change climate in two ways. One is fast and short, the other is slow and long. The short way comes from sulfur-rich blasts that send gas high into the stratosphere, the dry upper air. There the gas turns into tiny droplets that reflect sunlight back to space. Less sun reaches the ground, so the surface cools for a year or two. History holds clear examples. In 1815, a tall mountain in Indonesia blew apart. The name is Tambora. The blast threw ash and sulfur very high. The next year, in parts of North America and Europe, was called the year without a summer. Frost hit crops in June. Snow fell in places where it should have been warm. Food prices rose. People moved. Earlier, in 1783, a long crack in Iceland poured out lava and gas for months. The event is called Laki. A blue haze spread across Europe. The air smelled of sulfur. Livestock died from fluorine-poisoned grass. The winter that followed was harsh. Closer to our time, in 1991, a mountain in the Philippines called Pinatubo blasted a tall ash and gas cloud. The tiny droplets spread around the world and lowered the average surface temperature by about 0.5 degrees Celsius for a short time. These events show how a volcano can reach beyond its valley, past its own skyline, and touch weather far away. The effect fades as the droplets fall out in a year or two. The slow way is through carbon dioxide, which warms the surface by trapping heat. A single eruption adds a small amount compared to what people add by burning fuels today. But over millions of years, steady volcanic carbon is a major part of the long climate balance. In deep time, long phases of strong volcano activity and wide lava fields line up with warm periods and stressed seas. In the other direction, when the planet was near a snowball state, slow volcanic carbon built up under all that ice and helped melt it back. Ash brings other short changes. When ash falls on snow and ice, it darkens the surface and makes it melt faster under the sun. When ash falls into the sea, it can feed tiny floating plants that then pull carbon from the air and carry it to the deep when they die. Gas can harm too. Sulfur can make acid rain for a while. Chlorine and bromine can affect the thin ozone layer in the high air if they reach it. These details matter most near the source. What matters for our story is that ash and gas tie volcanoes to air and water far from the vent in ways that are at once brief and strong and then pass, leaving the slow carbon loop to steer the long path again. Earth is not a stone statue. It is a slow machine that grinds, melts, lifts, and rebuilds its own surface. Volcanoes are the heat vents and the brick makers in this machine. Think about a lava flow that cools into dark, hard rock. Sun, rain, wind, ice, and roots break that rock into grains. Rivers carry the grains to lakes and seas. Layer by layer, mud and sand pile up. The weight of new layers squeezes the ones below. Water moves through the pile and leaves minerals behind that glue the grains. A soft layer becomes stone. Later, the slow push of plates raises that stone into hills and mountains. While this lifting goes on, some of the buried rock is pushed deep enough to warm and change. New minerals grow. Some water is driven off. The rock becomes tougher and more dense. If it goes deeper and gets hotter still, it starts to melt. Melt is lighter than the rock around it, so it rises. It gathers in pockets. It feeds volcanoes. When it reaches the surface, it cools into fresh rock again. The loop starts over. This loop is the rock cycle. Volcanoes are in the middle of it because they turn deep, hot material into new crust at the top, and because their heat helps drive changes below. Without volcanoes, you would still get some sand and mud from the tiny breaks that happen in any rock, but there would be no constant supply of new crust to balance the loss. The world would scab over and grow old. With volcanoes, the world stays young. On the ocean floor, this is easy to see. Ridges make new crust. That crust moves away, cools, grows heavy, and finally sinks in trenches. In the sinking slab, water and other light materials leave and help the mantle above to melt. The melt rises and makes arcs of volcanoes and new light crust. On continents, the story is more complex, but the idea is the same. Magma adds light rocks that float high. Uplift makes slopes. Slopes feed rivers. Rivers carry grains that become new stone. Then deep heat and pressure change that stone, or melt parts of it, and the cycle continues. Volcanoes also set the clock for parts of this cycle. Fresh lava is like a clock that starts at zero because we can measure how long its atoms have been cooling. Layers of ash in old riverbeds are timestamps that link land records to the records in the sea. In this way, volcanoes are not only builders, but also markers that help us read the book of Earth. The quiet truth is that every field, hillside, beach, and cliff you pass has in it some ash or lava from ancient eruptions, ground down and mixed and turned over many times. The ground beneath your feet is a quilt, and volcanoes stitched most of the pieces. Water is not only in oceans, rivers, ice, and clouds. A great deal of water is locked inside minerals in the crust and the upper mantle. The seafloor forms at ridges as hot lava cools in contact with seawater. Cracks open as the new crust shrinks. Cold water pours in. It reacts with the hot rock and becomes part of the minerals there. When that seafloor grows old and heavy and sinks at a trench, it carries this stored water down. As the slab goes deeper, it warms. The minerals that held water are no longer stable. They break and make new ones that hold less water. The extra water escapes upward into the mantle above the slab. Even a small amount of water lowers the melting point of hot mantle. Rock that was almost solid now melts a little. That melt rises and feeds volcanoes in the arc above. This is why arcs tend to make sticky magmas, why they build steep cones, and why they explode more often. Water in the melt makes gas bubbles that grow as pressure drops, like bubbles in a soda bottle. If the melt is sticky, the bubbles cannot escape easily. Pressure builds until it blows the top off. Water also softens the crust. It helps rocks bend instead of snap, which makes room for magma to rise and collect. Some of the water that came down in the slab goes back up in volcanic gas. Some is trapped again in new minerals and carried back down. This slow shuttle is the deep water cycle. It is linked to sea level and ocean chemistry over long time. When there is a lot of new seafloor being made and sunk, more water is pulled down. When the rate slows, less is pulled down and more stays in the oceans. On a planet with no plate motion, most water would sit in the surface pools and in the air. With plate motion and subduction, some water spends time in a deep loop. This loop is part of what keeps the mantle soft enough to flow. Water at tiny amounts makes a big change in how mantle rock creeps. So water not only feeds melt, it also greases the slow gears that move the plates. In this way, volcanoes, oceans, and plate motion are tied together by the quiet work of an invisible traveler that rides minerals down and gas up, again and again across the ages. Not all volcanoes look the same because not all magmas act the same. Thin, runny basalt comes from mantle melt that rises fast and does not carry many crystals. It flows easily and spreads far. Where basalt erupts often from a few vents, It builds wide, low shields with gentle slopes. The islands of Hawaii are shields. They grow by many stacked flows that look like dark ribbons on a globe. When basalt erupts in short bursting fountains, it throws clots of lava that land near the vent and make small steep cones of loose rock. These are cinder cones. They are common around larger shields and in rift zones. Sticky magma rich in silica behaves very differently. It moves slowly, traps gas, and tends to pile up over a vent. Over many cycles of growth and blast, it builds a tall cone with steep sides made of layers of lava, ash, and broken rock. These are composite volcanoes. The Andes and Japan have many of them. Their slopes hold glaciers and forests. Their valleys are deep and often carry rivers fed by snow and rain. Composite volcanoes can lose a side in a fast collapse if the inside of the cone weakens. Mount St. Helens did that in a famous event. Some sticky magmas never flow far. They ooze and make rounded hills called domes. Domes can break and cause hot rock falls and small fast clouds that rush down gullies. When huge volumes of sticky magma erupt in a short time from a shallow chamber, the roof falls and makes a broad low basin called a caldera. Later, small domes and flows rise inside the basin, and lakes and plains fill the rest. These shapes age in different ways. Basalt plains crack and form steps. Water cuts narrow canyons. Plants spread fast because soils form quickly on basalt. Steep cones erode into sharp ridges and V-shaped valleys. Rivers move ash and boulders to fans on the low ground. Glaciers carve bowls high on the flanks. Calderas become patchworks of lakes, wetlands, meadows, and dark glassy lava domes. Many towns sit on the flat floors because the land is fertile and level. Lava also shapes coasts. Where flows reach the sea, they build new land in black ledges that steam and hiss. Wave action breaks the new rock into black sand that forms fresh beaches. Over long time, if the land around a volcano sinks a little while, a coral reef grows upward. A ring of coral can stay at sea level while the volcano in the middle wears down. The ring remains as an atoll around a clear lagoon. This idea was first explained in simple terms using careful notes of island chains that show young high islands at one end and low rings at the other. In short, magma type sets the shape, eruptions set the layers, and weather and waves carve the finish. The landscapes we love around volcanoes are the quiet sum of flow, blast, lift, and rain. Some eruptions are woven into our stories because they touched many lives and left marks we can still see. Krakatoa in 1883 sat on an island strait between two large islands. It had a series of blasts that ended in a final huge one. The sound was heard far away. The sea rushed back and forth. Waves rose high and swept coasts. Ash fell across wide areas. The sky around the world glowed strange colors at sunset for months, as tiny particles spread in the high air. Trade and travel slowed. Many people died on nearby shores. In 1902, on the island of Martinique, a glowing ash cloud raced down from a cone called Mount Pelee and overwhelmed a city within minutes. It showed how fast hot ash and gas can move and how they flow like water down valleys. In 1980, a mountain in the Pacific Northwest gave a lesson in the danger of sideward blasts. The north flank of Mount St. Helens slipped. Pressure dropped in the magma. The mountain blew out sideways and flattened forests. A tall grey column then rose and dropped ash across many states. Scientists learned a great deal because they were watching closely. In 1991, Pinatubo in the Philippines warned people for weeks with more quakes and swelling ground. Many left in time. The main blast sent sulfur into the high air and cooled the whole planet for a short time. In Iceland in 2010, a small volcano under a glacier sent ash high into the flight paths over the North Atlantic. Planes were grounded for days. This showed how even a moderate event can ripple through a modern world that depends on clean air corridors. In each of these cases, careful records help today. They tell us which signs came early, which areas suffered most, what simple steps saved lives, and how far effects can spread. They also show the mix of gifts and risks. The same forces that spread ash and cut forests also build rich soils, make hot springs, and shape islands and valleys that people love and use. When we speak of famous eruptions, we should tell the whole story. We should name the warnings that were seen, the warnings that were missed, and the ways people helped each other. We should honor the loss and also the lessons that now protect other towns under other peaks. The ground speaks before it moves. Our job is to listen and act with care. Large calderas and old thick ash layers can stir fear because they hint at power beyond our daily scale. Stories grow around places like Yellowstone in North America or Toba in Indonesia. The word supervolcano is used in many headlines. The calm facts are these. Very large eruptions have happened, but they are rare on human timescales. They build over long periods. They require a wide, shallow chamber of sticky magma that gathers gas and heat. They show years of change in ground shape, quake patterns, and gas before a main event. Most of the time, those changes rise and fall without a large blast. At Yellowstone, the ground breathes up and down by small amounts as water and heat move. Geysers shift and steam holes change, but the system often relaxes. Careful studies of old ash and lava show that the big events there are separated by many hundreds of thousands of years. The last one of that size was far older than any city on Earth today. Toba did have a very large eruption tens of thousands of years ago. Some older writing claimed it nearly wiped out people. Newer studies of tools and fossils suggest people survived in many places, though there may have been a short chill in climate. These updates remind us to check stories with data. A large event would be serious for a wide region, but it would not end all life, and it would not arrive without strong warnings. Scientists watch these places with networks of seismometers, GPS, gas sensors, and satellites. Plans exist to move people if needed. At the same time, many medium-sized caldera eruptions in history matter more for nearby towns than any rare giant. Those can still blanket farms in ash, push rivers into new paths, and drop roofs if people do not clear them. Good maps and drills reduce those risks. The right way to think about rare giants is like this. They are part of Earth's deep breathing. They happen now and then over a very long story. They leave beautiful lands filled with lakes and meadows. They power geysers and hot springs that draw visitors, and also provide hot water for heat and power. We should respect them, learn their signs, and live our lives without fear, because daily risks we can control are much larger than the odds of a giant blast in any given lifetime. Volcanoes do not only make land, they also stock it with useful gifts that people rely on every day, often without noticing. When hot water moves through young volcanic rock, it dissolves small amounts of metals from the rock around it, then cools and drops those metals again in cracks and pores. Over long time, this slow flow builds rich veins and layers that people later mine. Many of the world's copper mines sit in belts that were once chains of volcanoes above sinking plates. The copper is spread through large bodies of rock near those ancient volcano roots, with a halo of other useful metals like molybdenum that help steel resist heat. In nearby zones where the hot water rose closer to the surface, the fluids cooled faster and dropped gold and silver in narrow fractures. These are the veins that once fed many mountain towns. Out at sea, hot springs on the deep floor spew metal-rich fluids that meet cold water and instantly form black clouds and piles of dark, heavy minerals. These piles are called massive sulfide deposits because they are made mostly of sulfur joined with copper, zinc and iron. Later, when a piece of seafloor is pushed onto land during a collision, those old piles can become mines in mountain belts. Not every gift is a metal. Volcanic glass, called obsidian, breaks with a sharp edge and once served as blades and arrow points. Pumice is a bubbly, light rock that can float. Ground up, it polishes and cleans. Bentonite clay forms when ash alters in water. It seals ponds and lines landfills. Pozzolan, made from volcanic ash, helps make strong cement that sets even underwater. These are quiet materials that let cities and farms work. The most widespread gift is soil. Fresh lava and ash weather into deep, rich ground that holds water well and feeds crops year after year. On these soils, people grow rice, coffee, grapes, bananas, and many other foods. That is why so many villages and cities sit on slopes with grand cones in view. The same ground that once ran hot is now the pantry of the valley. Beneath the fields, the rock holds water in its cracks and holes. Thick piles of old lava flows make good aquifers, which are underground stores of fresh water. Rain sinks in through broken tops of flows, moves slowly inside the stack, and emerges lower down as steady springs that supply towns even in dry months. Where the deep heat is still close, people can also tap the warmth itself. Geothermal power is the use of Earth's heat to make electricity and to warm buildings. There are a few main ways to do it. In rare places, steam rises on its own from the ground at a high enough pressure to spin a turbine. More often, very hot water is pumped up from wells, flashed into steam as pressure drops, and run through a turbine before being cooled and sent back down to keep the reservoir healthy. In cooler fields, a closed fluid that boils at a lower temperature than water is heated by the groundwater in a heat exchanger and then drives the turbine. The used fluid is cooled and cycled again. The groundwater is re-injected, so the system does not run dry. Countries that sit on active belts use this power widely. Think of Iceland, where hot water from volcanic ground heats homes and pools, or Kenya and Ethiopia in the Great Rift, or New Zealand and parts of California and Italy. Done well, this power is steady and clean, with a small land footprint. It needs care because pulling too much heat or fluid too fast can let the ground cool or subside, and any gas in the water must be handled so it does not reach the air. But the basic idea is simple. The same heat that once drove lava to the surface can turn a turbine today and light a school at night. In this way, volcanoes are not only the builders of old lands, but also partners in the quiet work of farming, mining, water supply, and gentle energy that helps people live well on the slopes they raised. To tell the story of volcanoes across deep time, we need clocks and pages. The pages are layers of rock. The clocks are tiny atoms that change at steady rates. When ash falls from the sky, it settles in a thin bed that stretches over a wide area. If that ash covers a forest floor, a lake bed, or the open sea, it forms a sharp line that marks a moment in time. Later, it may turn into a hard layer, but the line remains. Far away, the same ash may sit between different kinds of local sediments, yet the line still links those places. This makes ash a bridge that ties many local stories into one wide story. To know the age of that ash, we turn to atoms that act like clocks. Some atoms are not fully stable. Over time, they change into other atoms at a known pace. This is called radioactive decay, which is a quiet, steady process, not an explosion. If you know the rate, and you can measure both the parent and the daughter atoms in a tiny crystal that formed in the ash while it was still hot, you can work out how long it has been since that crystal cooled. Different atom pairs work over different spans of time. One common pair for young ash uses an atom in the potassium family that slowly turns into argon gas locked inside crystals. Another pair for older rocks uses uranium slowly becoming lead inside hard, clear crystals of zircon that grow in sticky magma. Zircon crystals are like tiny vaults that keep their records well. In the sea, iron in new lava lines up with Earth's magnetic field as the rock cools. The field has flipped many times, so the seafloor holds a barcode of normal and reversed stripes on each side of the ridge. We matched those stripes with ages from other methods and learned the spread rate of each ridge through time. On land, long lava flows and ash beds can be dated the same way, then matched to changes in fossils above and below. This lets us tie the fire record to the life record and see how big lava fields line up with stress in the oceans and on land. We can also look into ice. Snow that fell long ago in Greenland and Antarctica is stacked in deep ice sheets with the oldest ice at the bottom. Fine ash and tiny sulfur droplets are trapped as layers. Counting layers and measuring sulfur lets us find single eruptions back many tens of thousands of years, and for the largest blasts even farther. Tree rings record the same short chills as narrow bands when summers were cool after a sulfur-rich eruption. Lake muds trap ash and also store thin dark lines from years when blooms of algae were strong, which can be tied to warmer or cooler periods. All of these are cross-checks. If the ash in a lake has the same chemical fingerprint as ash in an ice layer, and both dates match a known historic event, we can trust the wider record. Using these tools, we know that large lava floods in Siberia began around 252 million years ago and lasted in pulses. We know that a wide field of lava-filled parts of 4 continents around 201 million years ago as the Atlantic began to open. We know that ash from a volcano in Alaska fell on the Great Plains 1,200 years ago, and that wind carried a fine veil as far as Europe after Tambora in 1815. These facts do not come from one source, but from many simple measures tied together with care. The story they tell is not one of constant disaster. It is a patient tale of bursts and rests, of belts that migrate, of seas that open and close, and of continents that grow ring by ring, all marked by thin lines of ash that let us turn stones into a readable book. Volcanoes will keep working as long as Earth keeps its inner heat, which is a very long time compared to human plans. The pattern may change in places as plates shift, seas widen, and mountains rise, but the basic engine will not stop. In cold places, thick ice can press down on volcano areas and hold them in a gentle grip. When ice melts after a long cold spell, that weight lifts and the crust relaxes upward. This small change in pressure can make it slightly easier for melt to rise and erupt. Studies from the end of the last ice age suggest that in some regions, eruptions became more common for a while after the ice pulled back. In the far future, if mountain glaciers and small ice caps shrink, this effect could play a small role around certain volcanoes. On the seafloor, changes in sea level also change pressure on ridges. A drop in sea level reduces pressure and can let more melt reach the surface for a time, while a rise does the opposite. These are quiet, slow links between water at the surface and fire below. Day to day, the future we can shape is about how we watch and how we build. Tools are far better than they were even one human lifetime ago. Satellites send down radar images that let us see the ground rise or fall by a few centimeters over wide areas. Small receivers measure how far they sit from the stars of the global navigation system and can detect how a volcano swells year to year. Networks of seismometers listen to tiny shakes that show how fluids move below. Gas sensors on the ground and in the air sample water vapor, carbon dioxide, and sulfur near vents because the mix can change as magma rises. Cameras watch cliffs where loose rock may fall, and thermometers watch hot springs. All these feeds go to teams who compare them with old patterns and with computer models that are really just careful math to test possible paths. Warnings can then be sent to people in clear words. The other half is planning on the ground. Towns can map zones where ash falls often, where fast hot flows have gone before, and where mud floods called lahars are likely if rain or melted snow mixes with loose ash. Rivers can be given clear channels to carry mud to safe plains. Bridges can be built with high, strong piers that let floods pass. Sirens and radio messages can be tested so that at night or in storms, the call still reaches homes. Schools can teach simple steps, such as keeping masks for ash and knowing the safe road that avoids valley floors. Land can be zoned so that heavy buildings do not sit in paths that past maps show as dangerous. This is not about fear. It is about respect for the ground and care for neighbours. At the same time, we can keep using the gifts. Geothermal heat can warm cities and make steady power with little smoke. Hot water from the ground can dry crops, run greenhouses, and draw visitors to spas that support families. Rich dark soils can supply food, and smart farming can keep that soil in place even during heavy rains by using terraces and ground cover. Good science and local wisdom work best together. People who live on a slope know where fog hangs, where snow melts first, and which ravines wake up in storms. Scientists bring maps and instruments. When both are heard, the valley stays safe. The road ahead is not to tame volcanoes. It is to live with them as past generations did, but with better eyes and faster messages, so that beauty and risk stay in balance. Let the whole story settle now like fine ash on still water. From a hot young world to the green and blue planet we know, volcanoes have been the steady workers. They raised the first high ground above a glowing sea. They breathed out water vapor and carbon dioxide and nitrogen to make a sky that could hold clouds and rain. The rain made oceans, and those oceans in turn helped make more melt where plates began to dive. Lava and ash piled up into islands and arcs welded onto light rafts that became continents. In the deep sea, ridges split and spread the floor, laying down new crust as fast as fingernails grow, day after day without sleep. At trenches, old floor sank back into the mantle, water came off the slab, and melt rose to feed chains of fire that built mountains and fed rivers with fine fresh grains. Hot spots burned trails across the plates, lifting shields from the sea, and where ridge and hot spot met, building whole islands on the plate edge. Sticky magma made tall cones, and in rare long moments, made broad calderas when much of a shallow chamber emptied and the roof fell. Over very long spans, great floods of lava poured from cracks and filled whole regions, shifting air and sea and life for a time before the world found balance again. All the while, rain and frost and roots broke rock, rivers carried sand to the sea, layers were buried, squeezed, warmed and changed, and some parts melted and rose again to start the loop anew. The rock cycle turned because volcanoes kept feeding it with fresh stone and heat. Life learned to use what fire made. In the deep ocean, where sunlight never comes, warm vents fed tiny microbes that ran on chemistry alone. On land, ash and lava became rich soils that grow food for millions. Springs and wells filled from cracks in old flows. Quiet gifts like pumice, clay from ash, and hard volcanic rock went into knives, soap, cement, and roads. In the air, volcanoes wrote both short and long notes. Short notes came from sulfur sent high into dry air, which cooled summers for a year or two and painted sunsets strange. Long notes came from steady carbon that, with weathering and shells and buried mud, kept a slow balance that held seas in liquid form across deep time. People learn to live on the slopes because the land is kind, and people learn to leave when a mountain sends warnings. We built better ears to hear small quakes. We made sharp eyes in the sky to watch a valley rise by the width of a finger. We learned to read the warm breath of a vent and the color of a spring. We laid out safe roads, strong bridges, and channels for mud. We trained for nights when ash falls and days when rivers run grey and fast. We also learned to use the heat. In many places, the ground warms homes, heats greenhouses, and turns turbines. None of this cancels the risk, yet it turns the place where fire once ran into a home filled with light and food and water. This is the shape of the story. Volcanoes built much of the ground we stand on, made much of the air we breathe, and still guide the long lines of climate and life. They are not only blasts on the news, they are slow makers, patient lifters, quiet feeders. When they wake, they speak first in small ways. If we listen, we can step aside and let them pass, then return to soil that is richer than before. If you are resting now, keep only a simple picture. Under your feet is a living engine. It moves heat upward. It makes rock and water trade places. It turns old stone into new land. It ties fire to rain and rain to life. It has done this for billions of years and will go on long after this night. Thank you for staying with me. May your thoughts drift like smoke that rises and thins, and may your sleep fall gentle as ash after a calm sunset over a quiet cone.